Hello everybody. In this video we'll be covering one of the sections in chapter 7 of our textbook entitled Chemical Reactions. In this video we're going to be discussing acid-base reactions. So let's review a few things that we know about acids. They have a sour taste. They're reactive with what we'll call active metals and not what we might call noble metals. So that means that they tend to react with metals like aluminum, zinc, and iron, but not with ones like copper, silver, or gold. And this is part of the reason why we reserve these for certain things like jewelry and stuff like that. They're going to tend to be non-reactive and not tarnish and stuff. That's like why we made pipes out of copper, for instance. This process of eroding away at metals is what we call being corrosive. They tend to react with carbonates to produce carbon dioxide. This is like the classic vinegar and baking soda reaction and stuff, and that liberates a gas, which is going to be important when we talk about gas evolution reactions. One chemical test I'll mention for checking for acids is the classic litmus test. This is where we take blue litmus paper, we add it to an acid, and it will turn it this pink reddish color. And acids react with bases to form ionic salts. Another byproduct is often going to be water. Here's a list of a lot of common acids, their chemical names, their formulas, and the old names for them or common names. And then this indicates whether or not they're a strong, moderate, or weak acid. Remember that we talked about how to write a acid name based on its formula, or its formula based on its name, in a previous section, and we discussed the strength of an acid when we discussed electrolytes. We haven't talked a lot about bases, but they do have some properties that are, analogous to the ones for acids. They tend to taste bitter. Most of the bitter flavor we have in a lot of our food comes from bases. They're caustic, which is similar to corrosive, but they tend to react with different materials. Caustic things will often liberate gases that aren't very pleasant to breathe in. They tend to feel slippery. Part of the reason why soap feels slippery is because it actually contains some bases inside of it. They turned the red type of litmus paper blue. So that's one of our classic chemical tests for that. And just like acids react with bases react with acids to form ionic salts. Here are some common base names. These are all various different metal hydroxides. We're going to kind of limit ourselves to talking about metal hydroxides when we talk about bases. And you'll notice that each one of these formulas has this OH group, and that is what defines it as a base, just like that free proton H group defined the acid. So this OH group is going to come off and dissociate into water, and it's going to have a negative charge, a -1 charge. There are many different common names for them, things that we actually are probably pretty familiar with. Lye has been used in soap making. Potassium hydroxide, this caustic potash, is used as a fertilizer. Milk of magnesia is magnesium hydroxide. And the ammonium hydroxide we talked before is a cleaner. When we add ammonia to water, we get ammonium hydroxide. And then we have their strength along here because these are electrolytes just like the acids were. So now that we've talked a little bit about the properties of acids and bases, let's look at the reactions that they have with each other. They're often also called neutralization reactions because the acid and base neutralize each other's properties. All right, so we wind up with something that is neither acidic nor basic. In the reaction of an acid with a base, the proton from the acid combines with the hydroxide from the base to make water. Okay. The cation from the base combines with the anion from the acid to make the salt. So we have a situation where we add acid to base and we get out a salt and water. Let's look at an example of that. If we had nitric acid and we reacted it with calcium hydroxide, what we're going to wind up making is calcium nitrate. And then these hydroxides are going to combine with those protons there to form water. When we have this guy here being aqueous, right, and we want to write the net ionic equation for this and the nitrate and the calcium nitrate ions become spectators, and our net equation is just that a proton has combined with a hydroxide ion to form water. And this is typically, these reactions typically are very reactive. They tend to happen pretty readily. And this is what's driving it. When we combine these protons and these hydroxide ions, we form water, which is very stable. This is going to release a lot of energy. And that is the force that's going to drive these reactions. To produce, let's go through the process for predicting the products of an acid-base reaction. First thing we want to do is determine what ions each aqueous reactant has. Then we're going to exchange those ions, okay? And we're going to want to make sure that we're combining our protons and hydroxides to make water. Then we're going to balance the charges of the combined ions to get a formula of the salt. Then we're going to balance the equation. And finally, we're going to determine the solubility of the salt. And we're going to use our solubility rules to do that. And we're going to recognize that if it's not soluble, we're going to get a precipitation reaction too. You'll notice that this seems very similar to our process for predicting solubility and precipitation reactions. And that's because basically a lot of these reactions are pretty much similar. There's some overlap between the two. Let's try one here. So let's write the molecular ionic and net ionic equation for the reaction of aqueous nitric acid with aqueous calcium hydroxide. First thing we need to do is write the formulas of the reaction. So we have to recognize that this is nitric acid and that this is calcium hydroxide. Then we need to determine the ions present when each reaction dissociates. So we're going to dissociate this down into its ions, dissociate this guy down into its ions. And then we need to exchange the ions. But we need to remember that when we have these protons and hydroxides, we're going to form a water. So when we do that, we get this as our product. We formed water from the protons and the hydroxides, and then we formed calcium nitrate. Then we're going to write the formula for the salt product. Okay, so when we have these two reacting together, we get calcium nitrate plus water. We need to make sure that this guy is a neutral species again, so don't forget to do that. And then we're going to balance the equation, okay? Maybe quickly balanced by matching the numbers of H and OH to make H2O. So if you only had two H's here, and so basically this guy had two hydroxides. That means that we needed two protons to balance that, and we're going to produce two waters in the end. Finally, we want to determine the solubility of the salt. Our calcium nitrate is soluble because all of our nitrates are soluble. And then we're going to write an S after an insoluble salt and AQ after a soluble salt. Now that we have the molecular formula for our reaction, we need to figure out what the ionic and net ionic equations are going to be. So we need to go through our steps for that. We need to dissociate all the strong electrolytes to get a complete ionic equation. We'll remember that the nitric acid is a strong acid, and that the calcium hydroxide and calcium nitrate, being a metal bound to nonmetals, are ionic, but not the water, because that's a liquid. So when we do that all out, we break them all up, we get this. Remember that we need to use our coefficients to have a balanced equation. And then we will eliminate our spectator ion. So that would be our calcium and our 2 nitrates. And we get this for our net ionic equation. Because we can divide each one of these coefficients by 2, we should do that, and we get this as our final net ionic equation. Here's a little practice for us. Let's see if you guys can complete and balance these acid-base reactions. I'll give you guys a moment to work on that. You can pause the video. So for the first one, we are going to be mixing these guys together. You can see that this guy has 2 protons and this guy only has 1 hydroxide, so we're going to need 2 of those. And we're going to wind up making ammonium sulfate and 2 water molecules in the end. For this guy, we have a situation where we have 3 hydroxides and 2 sulfates. So we have to account for that, right? We need to do the 2 here so we get 6 and 3 here so we get 6 protons. And in the end, we're going to produce this guy here, aluminum sulfate. We're coming up with this equation by balancing the charges again. Remember, aluminum has a +3 and the this is a sulfite. The sulfite has a -2 charge. And we end up producing 6 water molecules. And for the last one, we mix barium hydroxide with sulfuric acid. We have 2 hydroxides here and 2 protons here, so we don't have any real balancing issues. And we wind up making barium sulfate and 2 water molecules.